A single red dot should not be able to shake our picture of the universe. It should be easy to name, easy to file away, easy to forget. But in James Webb's deepest images, some of the smallest points of light are refusing to behave like stars, refusing to look like galaxies, and refusing to fit the timeline astronomers expected. They may be ancient galactic seeds, packed with young stars, hiding in plain sight like cosmic embers from the dawn of time. If this kind of quiet mystery is the reason you love space science, a gentle like, a subscription, or sharing this video with another curious mind helps this channel keep exploring the dark more slowly and deeply. Thank you for giving your time to watch and listen. And wherever this finds you, what time is it there? And where in the world are you watching from? Leave it in the comments. Now, let the first red point open the door. Astronomy begins with separation. A star is understood as a point, a compact source of light whose glow comes from a single sphere of plasma or from a small system of stars bound closely together. A galaxy is understood as something broader, a structure with depth and extension, a vast arrangement of gas, dust, dark matter, and many stars spread across distances so large that ordinary language begins to soften around them. These categories are not only names, they are practical tools. A telescope does not receive labels from the universe. It receives light, faint and stretched and altered by distance, and astronomers must decide what kind of object sent it. For generations, the distinction seemed simple enough. Stars looked sharp. Galaxies looked diffuse. Stars appeared as small points against darkness. Galaxies appeared with haze, with edges, with hints of arms or bulges or irregular clouds. Then, the James Webb Space Telescope looked into one of the deepest windows of the sky and found objects that troubled that old division. They were not broad smudges. They were not graceful spirals or pale elliptical glows. They appeared as tiny red points, almost too small to deserve attention, as if the telescope had captured a few stray embers scattered across the background of the image. Yet the light from these points did not behave like the light of nearby stars. Their color suggested great distance. Their spectra suggested chemistry and star formation. Their brightness, when translated across cosmic time, suggested something far heavier than a single star. In ordinary images, they resembled foreground points. In physical meaning, they carried the weight of galaxies. The mystery begins in this mismatch, where appearance and identity no longer agree. The early universe is not expected to be tidy, but it is expected to follow certain broad rules. Matter gathers under gravity. Gas cools. Stars ignite. Galaxies grow from small beginnings, slowly assembling their mass through collapse, inflow, and merger. The farther back a telescope looks, the younger the universe becomes, and the more unfinished its structures are expected to appear. This is why deep-field images carry a special tension. They are not only pictures of faraway places, they are pictures of earlier stages. A faint red galaxy in such an image is not merely distant, it is young in the cosmic sense. Seen before, later, growth could shape it. The James Webb Space Telescope was built for this territory. Its mirrors and infrared instruments receive light that has been stretched by the expansion of space. Light that began as visible or ultraviolet glow in the early cosmos and arrived much later as infrared warmth. In this kind of observing, red does not simply mean color. It can mean time. It can mean that the object belongs to an era when the first large structures were still taking form. The tiny red points in these images, therefore, became more unsettling the more carefully they were examined. If they were local stars, their point-like appearance made sense, but their colors and spectra did not. If they were distant galaxies, their colors made sense. But their point-like appearance became difficult to explain. A distant galaxy should usually spread its light across several pixels. Even if only faintly, it should show some width, some soft edge, some hint of being made of many sources blended together. These objects held their light close. They seemed condensed to the limit of the telescope's vision. The instrument treated them as points because, for Webb, they were almost unresolved. The universe was presenting something massive in the visual language of something small. The first deep images from Webb were filled with obvious wonders. Gravity curved the light of background galaxies into arcs. Ancient systems appeared as red smudges behind younger clusters. The sky seemed layered, with foreground galaxies, magnified background galaxies, and still deeper objects packed into the same field. In that visual abundance, the smallest points were easy to overlook. A deep field image naturally draws attention toward form. The eye seeks spirals, lenses, sweeping distortions, and luminous knots. A tiny red speck does not announce itself. It does not look like a revelation. It looks like a nuisance, a foreground star, a detector artifact, or an ordinary faint source among thousands. Astronomy has long depended on filtering such nuisances away. The sky is full of objects that interfere with the desired signal. A star in the Milky Way can sit directly in front of a faraway galaxy. A cool dwarf star can glow red in a way that resembles a distant source. A brown dwarf can masquerade as something ancient. Because enormous surveys contain more sources than any human can inspect one by one, computer methods help sort them. Objects that appear sharp and point-like are often treated as stars unless other evidence says otherwise. This habit is reasonable. It protects researchers from wasting time on foreground clutter. But reasonable habits can hide unreasonable objects. The little red points now under scrutiny are troubling because they exploit that habit. They look like the kind of thing astronomy learned to discard. Their importance is not visible in their shape. It is carried in their color, in their spectral fingerprints, and in the contradiction between their apparent simplicity and their inferred distance. This is what makes them powerful as a discovery. They do not arrive as dramatic structures. They arrive as almost nothing. A single point of red light can contain an entire argument about how galaxies begin. The more these points are studied, the less they resemble simple foreground mistakes. Their story depends on more than image shape. Spectroscopy, the splitting of light into its component wavelengths, turns a dot into a diagnosis. It reveals which atoms are present, how the light has been stretched, and how rapidly the emitting gas is moving. In the case of the strange compact red objects, some signs point toward starlight and ionized gas rather than the violent environment around an active black hole. Their light carries the suggestion of young stars packed into an astonishingly small region. If that interpretation is correct, then the telescope is not seeing a black hole pretending to be a galaxy. It is seeing a galaxy pretending to be a star. The phrase sounds almost impossible, but it captures the heart of the problem. A galaxy is usually imagined as spacious. Even a dwarf galaxy has room inside it for vast separations between stars. These objects appear to compress galactic meaning into a scale that challenges intuition. They may contain enormous amounts of stellar mass within a region so compact that, across immense distance, it collapses into a point. The sky does not reveal them as miniature spirals or young, sprawling systems. It reveals them as red seeds, dense and unresolved, as if the central core of a galaxy had appeared before the larger galaxy around it had time to unfold. Such objects are sometimes compared to platypuses, not because the name is technical, but because the confusion is familiar. The platypus unsettled older categories by combining traits that seem to belong to separate branches of life. These compact red sources unsettle astronomical categories in a similar way. They carry the appearance of stars and the implications of galaxies. They are small to the eye and large in consequence. Their strangeness does not come from spectacle, but from refusal. They refuse to stay in the box assigned by their shape. They refuse the old confidence that a point is merely a star unless proven otherwise. In the deep universe, a point can be a crowded city of newborn suns. A speck can be the visible surface of a process that occurred when cosmic history was still young. This is why the discovery feels mysterious in a deeper sense than surprise alone. It is not only that Webb found something unusual, it is that the unusual thing was hiding under a familiar disguise. The telescope did not merely push farther into space. It exposed a weakness in the way the sky had been read. For years, perhaps decades, similar objects may have passed through images and catalogs as uninteresting points, removed by software or ignored by selection rules. The universe may have placed a population of early compact galaxies in plain view, and astronomy may have mistaken them for foreground clutter because they wore the visual mask of stars. Webb's power lies partly in sensitivity, partly in sharpness, and partly in the patience it gives to faint infrared light. But the instrument alone does not complete the discovery. The final step is an act of interpretation, a willingness to look again at what seemed too small to matter. In that sense, the hidden red points are not just objects in the early universe. They are lessons in humility. They show that classification is only as strong as the assumptions beneath it, and that the first galaxies may not always have looked like young versions of the galaxies known today. Some may have begun as dense, luminous cores, quietly gathering matter, forming stars with extreme efficiency, and waiting for later time to build the larger structures around them. The red points remain uncertain as more spectra are gathered and more fields are searched. Yet the challenge is clear. A telescope found sources that look like stars, sit at distances where stars should not appear that way, and speak with the chemical and energetic language of galaxies. At the edge of the observable past, the universe has placed a riddle, a dot of red light that should be ordinary, but is not. The first image from the James Webb Space Telescope did not look quiet. It looked crowded with time. At the center was a massive galaxy cluster, a congregation of galaxies whose combined gravity had curved the space around it into a kind of natural lens. Behind that cluster, much farther away, older and fainter galaxies had sent out their light long before Earth had cities, long before Earth had animals, and in some cases, long before the sun had formed. As that light crossed the warped space around the cluster, it bent, stretched, and brightened. The result was a field of strange beauty. Galaxies appeared as arcs, threads, smears, and glowing fragments, some magnified by gravity into forms they would never have shown on their own. The image carried the emotional force of a first opening. It was not simply a sharper version of what older telescopes had seen. It was a deeper style of looking, tuned to infrared light, able to receive ancient signals that had been stretched by the expansion of the universe until they became invisible to human eyes. In the public view, the attention naturally moved to the large shapes. They were easier to understand. A curved arc told a story of gravitational lensing. A spiral told a story of rotating gas and stars. A bright elliptical form told a story of age, mass, and merger. The mind wanted to rest on structures with shape. It wanted galaxies that looked like galaxies. Yet the real mystery in that image was not only in the grand patterns, it was also in the small red flecks scattered between them. the sources that seemed too slight to interrupt the spectacle. They were the sort of marks a viewer might mistake for imperfections in the picture. Tiny points left behind by the machinery of observation. Their silence was part of their disguise. Deep-field astronomy has always depended on patience with the faint. The most distant objects rarely announce themselves as grand structures. They are small, dim, and often ambiguous. The difficulty is not simply finding light. It is deciding what kind of light it is. In the Webb deep field, a foreground galaxy and a remote early galaxy may share the same image, separated not by position on the screen, but by billions of years of cosmic history. A star in the Milky Way may sit in front of everything, a nearby speck placed by chance along the line of sight. A detector may carry tiny artifacts. A faint source may be stretched by lensing, reddened by dust, or reddened by distance. Every dot asks for interpretation. The cluster made the interpretation even more layered, because its gravity acted as a magnifier and a distorting mirror at the same time. Some objects behind it became easier to see, but their shapes were altered. Some were duplicated. Some were stretched into crescents. Others remained unresolved, appearing as compact points that held their meaning in color rather than form. This is why the red specks mattered. They did not compete with the arcs and spirals by size. They challenged the image in a different way. The eye could pass over them, but the data could not dismiss them so easily. Their color placed them among objects that deserved attention. Their compactness placed them among objects normally removed from consideration. They occupied the uncomfortable space between a foreground nuisance and a distant discovery. New instruments often reveal not only new objects, but old habits. Before Webb, the Hubble Space Telescope had already shown that apparently empty patches of sky were packed with galaxies. But Webb saw differently. It reached into the infrared, where ancient starlight, stretched by cosmic expansion, had come to rest. This made certain sources appear that were previously too faint, too red, or too confused with noise. The red points belonged to this change in perception. They had the surface simplicity of stars. But Webb's infrared sensitivity allowed their deeper strangeness to rise. They had no obvious arms, no visible disks, no broad glow that gave them away. In a sky trained by experience, they seemed almost disqualified from being galaxies before the question could even be asked. But a telescope does not know human categories. It gathers photons. If the photons come from a compact swarm of early stars, the telescope will record a point. If they come from a nearby cool star, it may also record a point. Shape alone cannot settle the matter. In the SMAC's deep field, this uncertainty became a hidden layer beneath the famous image. What looked like a background of minor red points may have included some of the most compressed galactic objects ever identified. Their smallness was not evidence of insignificance. It was part of the clue. The visual drama of the image therefore created a paradox. The more beautiful and complex the large structures appeared, the easier it became to overlook the objects that did not participate in that beauty. Human attention is not neutral. It follows contrast, symmetry, and scale. It favors what can be named quickly. The arcs of gravitational lensing were immediately recognizable as evidence of mass-bending light. The spiral galaxies were immediately legible as cosmic architecture. The red points were less generous. They offered no shape to interpret. They gave almost no spatial information. They were closer to punctuation than illustration. Yet punctuation can change the meaning of a sentence. In a deep field image, a point source with the wrong color can change the meaning of a cosmic era. If such points are truly distant and galactic, then the early universe was not only forming extended systems through gradual assembly, It was also making dense, luminous cores so compact that even Webb could not easily spread them out. This would mean that some of the first significant stellar systems did not resemble young, loose galaxies, but bright knots of intense formation. They may have been the beginnings of larger galaxies, caught before later growth expanded them into familiar forms. The first Webb deep field, then, was not only a picture of what the universe looked like, it was a test of what astronomers expected a galaxy to look like. The field itself was also a lesson in scale. The patch of sky was tiny, small enough in everyday terms to seem almost nothing. Yet within it were thousands of galaxies, some nearby by cosmic standards, others far enough away that their light carried news from the universe's youth. A narrow view can contain a history almost too large to hold in thought. The sky does not need a wide opening to become vast. A small opening, if deep enough, becomes a tunnel through time. In such a tunnel, the foreground and background are layered so densely that ordinary distance breaks down. Everything appears together, though it belongs to different ages. The red specks lived inside this layered confusion. Some may have been ordinary sources. Some may have been misread. But some stood apart because their properties did not fit the expected filters. They were read in a way that suggested the long stretching of light. They were compact in a way that suggested either nearness or extraordinary density. They sat behind the gravitational architecture of a cluster that could make distant objects brighter and more visible, while also complicating measurement. This is what made the first discovery environment so treacherous. The image gave access to ancient light, but it also demanded caution. A red point could not simply be called a galaxy because it was interesting. It had to survive other explanations. It had to be compared against cool stars, brown dwarfs, dusty galaxies, active black holes, and instrumental effects. The mystery grew not from a single glance, but from the failure of the easiest answers. As astronomers returned to the data, the deep field changed character. It was no longer only a celebration of Webb's sharpness. It became a map of overlooked possibilities. The question moved from what can be seen to what has been trained out of sight. When images are processed and searched, sources must be sorted. The grand structures are often preserved because they fit the search. The point-like sources are often filtered because they seem local, common, or irrelevant. The first deep field revealed how dangerous that sorting can become when the early universe produces objects that imitate the foreground. The faint red points were not hiding behind dust clouds or beyond the telescope's reach. They were hiding inside a category. They were concealed by the assumption that important galaxies should be extended. In this way, the image that seemed to reveal everything also reminded astronomy how much revelation depends on attention. Webb provided the sensitivity, but the mystery required someone to ask why certain points had been ignored. The spectacular arcs and galaxies were genuine wonders, but their grandeur made the tiny objects seem secondary, and they may have carried a more disruptive message. They suggested that the early universe could build galactic seeds in forms too compact for traditional visual recognition. They suggested that a deep image is not exhausted by its obvious beauty. Its most important evidence may sit between the famous structures, in quiet red marks that wait for a different question. The SMACS field remains a doorway into ancient space, but it is also a mirror held up to the habits of science. It shows that the universe can place a major discovery in the margins, not by making it invisible, but by making it look familiar enough to ignore. Objects that do not fit a search are often lost before they are studied. Modern astronomy depends on this kind of loss, not because astronomers are careless, but because the sky is too full to inspect without rules. A deep image from a powerful telescope may contain thousands of sources, each one a small measurement of light, color, position, and shape. Some are foreground stars in the Milky Way. Some are distant galaxies. Some are detector artifacts, cosmic ray strikes, blended systems, or patches of noise strengthened by processing. To turn such an image into science, researchers must build catalogs. They must decide which sources are real, which are useful, and which belong to the background clutter of the observation. The decisions are made with software, with statistical thresholds, with models of how a telescope spreads the light of a point source, and with the older expectations that have guided astronomy for decades. A source that appears sharp and unresolved is normally placed into one mental category. It is likely a star. A source that appears soft, widened, or structured is placed into another. It is likely a galaxy. These rules are efficient, and most of the time they work well enough. Without them, every deep survey would become unmanageable. But every rule creates a shadow. It defines what will be kept, and it also defines what will be thrown away. The compact red objects found in Webb images seem to live in that shadow. They occupy the form of things that are routinely removed and the physical meaning of things that should be preserved. They are the kind of sources an algorithm learns to distrust. In an image, a nearby star is not always a simple dot. Because of the shape of a telescope and the way light moves through its mirrors, the star becomes a point spread pattern, a small central peak with characteristic wings and, in Webb images, sharp diffraction spikes. These spikes are not part of the star itself. They are the signature of the instrument. They tell astronomers that the source is so compact that the telescope cannot resolve its surface. For most purposes, this is a useful warning. A point-like object with diffraction spikes is probably not a remote sprawling galaxy. It is probably a star in front of the real subject. Programs that sort astronomical sources can therefore use compactness as a shortcut. If the light profile matches the telescope's point source pattern, the object can be marked as stellar and excluded from a galaxy sample. This protects studies of distant galaxies from contamination by nearby objects. It keeps the catalogs cleaner. It reduces false discoveries. Yet the strange red sources discovered in Webb data turn that same shortcut into a trap. They look point-like because they are compact, but their compactness may not come from nearness. It may come from extreme density at immense distance. The telescope sees them as points for the same reason it sees stars as points. But the physical situations are opposite. One is small because it is a single nearby object. The other may be small because an entire early galactic core is packed into a region too tiny for the telescope to spread apart. The image alone cannot tell the difference. A sorting rule built for ordinary cases can quietly misclassify the extraordinary one. Color adds a second layer to the problem. Cool stars and brown dwarfs in the Milky Way can appear red or infrared bright. They are faint, low-temperature objects, glowing more strongly at longer wavelengths than in visible light. A distant early galaxy can also appear red, but for a completely different reason. Its light began at shorter wavelengths and was stretched by the expansion of space during the long journey to the telescope. Dust can redden a galaxy as well, absorbing bluer light and letting redder light escape. This means redness is not a single clue with a single meaning. It is a shared mask worn by several kinds of objects. An algorithm looking for distant galaxies must separate red because of temperature, red because of dust, and red because of cosmic expansion. The compact red Webb sources complicate this task because they combine the shape of a foreground object with the color of something ancient. In many search pipelines, that combination may not survive the first pass. A point-like red source can be dismissed as a cool dwarf star before its deeper possibilities are examined. This is not a failure of intelligence. It is a consequence of probability. Most such objects in many fields really are mundane. The rare object that is not mundane must survive rules designed around the common case. Scientific methods are built to reduce error. But there are different kinds of error. One kind is accepting a false object as real. Another is rejecting a real object because it looks too much like a false one. Astronomy has usually feared the first error more visibly. A claim about a distant galaxy can be damaged if the object turns out to be a nearby star. So, surveys apply conservative cuts. They prefer clean samples, even if that means losing some unusual sources. This is understandable, especially when researchers are measuring populations, rates, and histories. A contaminated sample can distort the result, but a too clean sample can also distort the universe. It may remove the very objects that do not fit existing categories. In the case of the compact red points, the danger is not that a few curiosities were missed. The danger is that a whole class of early galaxies may have been systematically undercounted because they resembled something astronomy was already trained to ignore. The phrase foreground clutter sounds harmless, almost administrative, but it carries power. Once an object enters that category, its story often ends. It becomes a thing in the way, not a thing in itself. This possibility changes the meaning of the archive. Older surveys may contain traces of compact early galaxies that were visible enough to be cataloged and then removed by selection criteria. They may sit under labels that do not match their nature, treated as stars, ambiguous sources, or failed candidates. The archive becomes not only a record of what was observed, but a record of how observation was interpreted. Webb is now forcing those assumptions back into view. The question is not only what new light the telescope can gather, it is what old light can mean when the filters of expectation are loosened. A source once discarded as too sharp may need to be reconsidered. A red point, once treated as local, may need spectroscopy. A faint compact object once ignored by a galaxy search may need to be restored to the story of galaxy formation. This is slow work. It requires comparing images across wavelengths, modeling how the telescope would see different kinds of sources, and testing whether their light can be explained by known stars, brown dwarfs, dusty galaxies, active black holes, or something stranger. The difficulty of this work gives the discovery its quiet weight. A dramatic claim can be made quickly, but a new population is built carefully. Each candidate must pass through doubt. Its position must be checked. Its colors must be measured. Its spectrum must be separated from noise. Its shape must be compared to the instrument's response. The goal is not to make every red dot mysterious. Most red dots will not be. The goal is to stop assuming that none of them are. That shift may sound small, but it changes the posture of the search. Instead of using appearance as a gate that closes early, astronomers can use it as the beginning of a question. A point can be asked why it has these colors. A spectrum can be asked why it does not match a cool star. A distance estimate can be asked why it makes compactness so extreme. In that patient sequence, neglect becomes discovery. The ignored source becomes evidence. The background pile becomes a place where the early universe may have hidden some of its densest beginnings. This lesson reaches beyond one class of objects. Science often advances by refining categories, but categories are never the universe itself. They are instruments of thought, shaped by what has already been seen. When instruments improve, the categories can become too small. A telescope like Webb does not merely add detail to familiar objects, it creates pressure on the definitions used to recognize them. If galaxies can be so compact, that they look stellar. Then, a visual boundary that once seemed natural becomes provisional. If the early universe can form dense stellar systems before they acquire broad visible envelopes, then the absence of fuzziness is not the absence of galactic nature. It may be a stage in galactic birth. The red points ask for this gentler kind of attention. They do not demand that every rule be abandoned. They ask that rules be remembered as choices, useful but incomplete. In the quiet machinery of data reduction, in the filters that remove point sources, and the catalogs that prefer clean shapes, a hidden population may have waited for a telescope sensitive enough and a question unusual enough to bring it back. The mystery is therefore not only in what James Webb found, it is in how easily it could have been missed. A universe filled with signals does not guarantee a universe understood. Understanding begins when the ordinary-looking dot is allowed to remain, just long enough for its light to tell a less ordinary story. The discovery did not begin with a grand shape. It began with a decision to look at sources that did not seem promising. In a field crowded with galaxies, arch, foreground stars, and faint background objects, the usual instinct is to move toward the obvious structures and away from the nearly featureless points. Ho Jingyan approached the problem from the other direction. He and his collaborators turned their attention to compact red sources, the kinds of objects that sit uneasily at the edge of a catalog. They were not spread out enough to look like ordinary galaxies, and they were not familiar enough to be dismissed without question. This was an unusual search because it treated ambiguity as a signal rather than a nuisance. The candidates were small, red, and easily confused with stars. But they also appeared in the kind of infrared data where the early universe leaves its faintest marks. The work required more than noticing a strange color. It required patience with the objects most likely to be filtered away, and a willingness to let their contradictions remain visible long enough to be tested. This is a quiet form of scientific courage. It does not announce itself as certainty. It begins with the suspicion that the discarded pile may contain something the main search was never designed to recognize. In the first stages, the sample was broad. Many compact red sources can appear in Webb images, and most of them will not be revolutionary. Some are probably stars in the Milky Way. Some may be brown dwarfs, dim objects too small to burn hydrogen steadily as true stars do. Some may be distant dusty galaxies whose light has been reddened by material within them. Some may be active galactic nuclei, where a black hole in the center of a galaxy dominates the light. A responsible search must begin by assuming confusion. It must not treat redness as proof of distance, or compactness as proof of strangeness. The team therefore had to sift. They examined many sources and narrowed them through color, brightness, shape, and spectral behavior. The goal was not to gather the largest possible list. It was to find the small set whose properties remained difficult after the ordinary explanations were applied. This is how a mystery becomes scientific. It does not survive because it sounds dramatic. It survives because simpler identities fail to absorb it. Out of a much larger collection of compact red candidates, a standout group emerged. Objects whose appearance suggested point sources, while their deeper information suggested something much more distant and complex. The smallness of the final group mattered. A weak mystery can be made by keeping every uncertain object. A stronger one is made by removing as many uncertainties as possible and seeing what remains. The sources that remained had a peculiar visual discipline. They did not spread themselves across the image in the comfortable way galaxies often do. They held their light close to the center, so close that they resembled the unresolved stars that clutter deep observations. Some showed the instrument's point source behavior. The pattern created when Webb receives light from something too compact for its mirrors to separate into a visible surface. In ordinary catalog work, this would have been a warning. It would have said that the object was probably nearby, probably stellar, probably not part of the distant universe at all. But their colors refused to complete that story. They were too red in the relevant bands, too consistent with light that had traveled across a large fraction of cosmic history. The contradiction became the object. A galaxy that looks extended may be interesting, but it does not challenge the method by which galaxies are recognized. A source that looks stellar and behaves galactic reaches deeper. It asks whether the way astronomy separates foreground from background can fail at the exact place where the earliest galaxies become visible. Yan's search was therefore not merely a hunt for rare objects. It was also a test of classification itself. The careful narrowing of candidates placed pressure on each possible explanation. If the objects were cool stars, their colors and spectra needed to match known stellar types. If they were brown dwarfs, their infrared behavior needed to follow the patterns such bodies produce. If they were quasars, the light should carry signs of violent gas near a feeding black hole. If they were ordinary galaxies, their shapes should be broader than points, unless their physical sizes were extraordinarily small. Each path demanded evidence. The strange sources did not cooperate neatly with any simple path. This is what made them valuable. They did not allow the search to stop at appearance. They required the team to move from the image into the physics of the light. In that transition, a red dot becomes less like a mark on a screen and more like a fossil of conditions in the young universe. Its color records expansion. Its spectrum records atoms and motion. Its compactness records either nearness or density. Only by bringing those clues together can the object begin to show its identity. The search also depended on a subtle change in attitude toward failure. Most candidate lists in astronomy are full of things that will later be explained away. This is normal. A strange source is not automatically a new class of object. It is a question waiting for cross-examination. Yan's approach did not need every candidate to be exotic. It needed enough of them to remain strange after repeated checks. This is why the work feels different from a casual scan of a beautiful image. It is systematic, but it is systematic in a way that protects the unusual. The team was not simply looking for what the software had been trained to call a galaxy. They were looking for objects that fell between the labels. The strongest candidates were those that held together under pressure, still appearing compact, still appearing deeply red, still refusing the usual stellar explanations. At that point, the mystery became more than a visual oddity. It became a possible population. A single object can always be an exception, a measurement problem, or an unlucky blend of effects. Several objects with related properties begin to suggest a process. Nature rarely produces one lonely riddle if the physics behind it is real. The phrase compact red source sounds modest, almost technical to the point of dullness, but in this context, it carries the whole disturbance. Compact means the telescope cannot easily resolve the object into a galaxy-like structure. Red means the light is either cool, dust-altered, or stretched by distance. Source means the object is first encountered only as received light, before its nature is settled. Each word contains uncertainty. Together, they define a place where the early universe can hide. The work of identifying such objects is slow because every shortcut is dangerous. A color cut may remove real distant galaxies. A shape cut may reject compact ones. A brightness cut may favor black holes over stellar systems. A catalog designed around familiar galaxies may miss the ancestors of those galaxies if those ancestors began as dense knots rather than wide disks. Yan's unusual search matters because it refused to assume that the first stages of galaxy formation had to resemble smaller versions of later galaxies. It allowed for the possibility that early galactic life could be stranger, denser, and less visually generous than expected. The result was a group of objects that seemed to stand at a boundary. They looked like points, but they could not be comfortably reduced to points in physical meaning. They were small on the detector, but large in implication. They were faint enough to have been missed by older instruments and compact enough to have been ignored by automated filters. Yet Webb's infrared vision gave them enough presence to be questioned. This is often how new classes enter science. They are not born from complete understanding. They begin as residues, as the leftover cases that do not fit, as sources that remain after the best explanations have done their work. Their first gift is confusion. Later, if enough evidence gathers, confusion becomes structure. A name follows. A theory follows more slowly. For these red objects, the nickname carries a certain gentleness, but the scientific challenge underneath is sharp. They may be telling astronomers that some early galaxies formed as dense stellar seeds, bright and compact, rather than as broad, visible systems. They may be showing that galaxy formation had a fast channel, one that built cores before building outskirts. Or they may reveal a different mixture of stars, gas, dust, and hidden engines that still has to be disentangled. The importance of Yan's search lies in preserving that uncertainty without letting it dissolve into vagueness. The candidates are strange for specific reasons. Their shapes, colors, and spectra create a pattern. Their pattern opens a path. Through that path, the most overlooked points in a deep image become possible witnesses to the first architecture of galaxies. The discovery, then, is not only an answer found in data, it is a change in where the question is placed. Instead of asking only which extended smudges are the youngest galaxies, the search asks which point-like sources have been pretending not to be galaxies at all. In that reversal, a faint red dot gains weight. It becomes a doorway into a time when the universe was still learning how to gather itself into lasting forms. Color is one of the quietest clues in astronomy, and one of the most powerful. A telescope receives light without context. It does not know whether a source is close and cool, distant and omniscient, or hidden behind dust. It only records how much light arrives in each wavelength. And from that pattern, astronomers begin to measure a history that may have taken most of cosmic time to unfold. The compact red sources found by Webb depend on this subtle language. Their mystery is not only that they appear as points, it is that they appear as red points in the infrared, with colors that do not sit comfortably inside the ordinary foreground story. A nearby star can be red because its surface is cool. A brown dwarf can glow mainly in infrared, and a dusty galaxy can look red because dust absorbs bluer light. But an object in the early universe becomes red for a deeper reason. Space itself has expanded while the light was traveling. The waves have been stretched during the journey, lengthened until light that began in a hotter, bluer form arrives as infrared glow. In this sense, redness can be a measure of distance, and distance can be a measure of time. The redder the ancient light becomes, the farther back the telescope may be looking, toward an era when galaxies were still in their first great season of formation. This is why the compact red points are so difficult. If they were merely nearby red stars, their point-like shape would be natural. If they are truly far away, their point-like shape becomes a clue to an extreme physical state. Redshift is the name given to this stretching of light. Cosmological redshift comes from the expansion of space between the source and the observer. As the universe grows, The path through which the light travels grows with it, and the light is drawn out into longer wavelengths. This makes the universe into a kind of time machine, not in the mechanical sense, but in the observational one. Looking far away means seeing light that left long ago. A galaxy seen at great redshift is not seen as it is now. It is seen as it was when that light departed, before later mergers, later stars, and later changes had time to occur. Webb was designed for this work because the earliest galaxies have had their light stretched into the infrared. For the strange red sources, this matters profoundly. Their light suggests that they may belong not to the nearby Milky Way foreground, but to a remote cosmic dawn. The same tiny dot on the image therefore changes identity depending on how its redness is understood. Nearby redness makes it ordinary. Distant redness makes it astonishing. The problem is that the image alone does not carry enough information to decide. The task is to combine clues until the possible identities narrow. Astronomers compare the brightness of the object in different filters, looking for the pattern expected when hydrogen gas absorbs light at certain wavelengths and when cosmic expansion shifts that break into the infrared. They ask whether the object disappears in shorter wavelength images and appears only in longer ones, a behavior that can suggest great distance. They compare it against known cool stars, whose atmospheres leave different patterns. They ask whether dust could imitate the signal, and whether a black hole could dominate the light. Each answer changes the scale of the object. If the source is local, it may be a small body glowing faintly in the foreground. If it lies billions of light years away, then even a small received signal can represent an enormous luminosity. Distance magnifies consequence. For the Webb sources, assigning great distance means accepting that the red points are not tiny in energy, only tiny in appearance. Their light has crossed so much expanding space that the compact dot becomes a messenger from a young and active universe. Once distance enters the interpretation, the contradiction sharpens. These objects may be located so far away that their light left when the universe was only a small fraction of its present age. In that early setting, there had not been much time to build large, mature structures by slow accumulation. Yet the brightness and inferred mass of the compact sources suggest a significant amount of stellar material. A distant object that looks like a point is not automatically physically small. It may simply be too far away for its structure to be resolved. But Webb is sharp enough that many galaxies at similar distances still show some extension or lensed shape. These particular sources remain stubbornly compact. If the redshift places them in the early universe, then their small image size implies that their stars may be packed into an extraordinarily tight region. They may be dense systems whose physical width is genuinely small compared with ordinary galaxies. The distance estimate, therefore, turns a visual detail into a physical challenge. What looks like a point may be a galaxy core with little visible outskirts. A young stellar city compressed into a space that would seem overcrowded even by the standards of dense star clusters. The light is ancient, but the structure it reveals may be intense, efficient, and startlingly concentrated. This is why redshift does more than locate an object. It transforms the meaning of its size. In everyday vision, a small apparent size usually means one of two things. The object is small, or it is far away. In cosmology, both may be true in different proportions, and the answer matters for theory. A compact object at modest distance can be unremarkable. A compact object at extreme distance, with the brightness of a galaxy and the spectrum of young stars, becomes a problem that must be explained. The measurements suggest that some of these sources are not just far, but far enough to belong to a time when conventional galaxy growth should still be underway. They seem to carry the mass and light of developed stellar systems without showing the spread that would make them visually comfortable. The redshift opens the ancient door, and the compactness refuses to let the object pass through as an ordinary young galaxy. It is the combination that matters. Red alone can mislead. A point alone can mislead. But a red point whose spectrum and colors keep pointing toward the early universe becomes a small, persistent argument against simple classification. The universe has made an object that appears nearby by shape and remote by color, quiet on the image and disruptive in calculation. Human senses evolved for nearby things. Distance in everyday life is measured by fading detail, by smaller apparent size, by softened edges. In the deep universe, those instincts begin to fail. An object can appear simple because it is beyond resolution, not because its nature is simple. A point of red light can hold 1 billion stars in possibility. A faint source can be bright beyond imagination when its distance is understood. A color can become a clock. Webb's infrared vision allows astronomy to read that clock with new care. But the reading is never automatic. It requires models of cosmic expansion, calibration of instruments, comparison across filters, and spectra detailed enough to separate one explanation from another. Every candidate redshift carries uncertainty. Some objects that seem ancient may turn out to be closer and dustier. Some may hide active black holes. But the existence of even a small set of robust, compact red sources is enough to widen the question. If they truly sit near the dawn of galaxy formation, then the early universe was capable of making extremely dense stellar systems sooner than expected. If many more are found, then the early census of galaxies must be revised, not only in number, but in form. The history of the cosmos would include a population of objects that were present in color, hidden by shape, and revealed only when distance was allowed to speak through redshift. The red points, therefore, serve as reminders that the universe often gives its most important evidence in indirect ways. It does not label an ancient galaxy as ancient. It stretches its light. It does not announce a dense core as dense. It leaves it unresolved. It does not explain whether a source is a star, a black hole, or a young galaxy. It lets the spectrum carry the answer, and even then only partially. In the case of Webb's compact red objects, the distance clue is the hinge on which the mystery turns. Without redshift, they are small red points, probably local and forgettable. With redshift, they become possible relics of a young cosmos, packed with stars and seen across a gulf of time. The same dot becomes either clutter or revelation. Its apparent smallness becomes not an ending, but the beginning of the question, far back in the infrared dark, where visible light has been stretched into a calmer glow. Webb has found sources whose redness pulls them toward the beginning, while their compactness pulls them toward impossibility. Between those two meanings, the mystery deepens. The simplest explanation for a bright, compact object in the early universe is often a quasar. This is not a careless assumption. It comes from a long history of finding distant points of light that, once examined closely, turn out not to be stars at all, but the blazing centers of galaxies. A quasar forms when a supermassive black hole feeds. Gas, dust, and torn stellar material fall inward, not directly into darkness at first, but into a rapidly rotating disk around the black hole. There, friction and gravity heat the material until it shines with extraordinary power. The region producing the light can be smaller than the galaxy that surrounds it, yet it can outshine that entire galaxy, to a telescope crossing billions of light years. Such an engine naturally appears as a point. It does not need to show spiral arms. A disk. or a broad stellar body. Its center overwhelms everything else. For the compact red sources found by Webb, the quasar idea therefore offered an immediate shelter. It could explain why something so distant looked so small. It could explain why a point source carried so much brightness. It could even explain why the early universe seemed to contain objects that were too intense for their apparent size. If a hidden black hole were doing the work, the stellar mass of a tiny galaxy would not need to carry the full burden of the light. The point would not be a compressed galaxy. It would be a lighthouse at the heart of one, powered by gravity rather than by ordinary starlight. The appeal of this explanation is strong because the early universe is already known to contain active black holes. Some quasars shine from astonishing distances, meaning their central black holes had grown large very early in cosmic history. This is itself a puzzle, but it is a familiar puzzle. Astronomers have spent years asking how black holes could gain so much mass so quickly after the Big Bang. And several possible paths exist. They may grow from massive seed black holes. They may feed rapidly in dense early environments. They may merge with other black holes as galaxies collide, because such engines are already part of the cosmic dawn. A red point in Webb data can reasonably be treated as a candidate member of that family. The visual resemblance supports the idea. A quasar does not look like a normal galaxy in a deep image. It looks almost stellar, a bright, unresolved point with the power of an entire system hidden inside it. The old name itself came from that confusion, from objects that looked star-like but were not stars. In that sense, the compact red sources seem to be stepping into a known pattern. A small, distant, a luminous point might simply be another active nucleus, another feeding black hole whose host galaxy is too faint or too compact to see clearly. This would be strange in detail, but not strange in kind. Science often begins with the explanation that demands the fewest changes to the existing picture. The quasar test matters because it protects the discovery from exaggeration. Without it, a compact red dot could be too easily turned into a new class of galaxy. But if the light is dominated by a black hole, the object belongs to a different story. The galaxy around it may still be present, but the observed point would be controlled by the central engine. Its size in the image would reflect the compactness of the accretion region, not the size of a stellar population. Its brightness would reflect the release of gravitational energy, not the combined glow of young stars. This distinction is crucial. Stars produce light through nuclear fusion, slowly converting hydrogen into heavier elements in their cores. Accreting black holes produce light through infall, converting gravitational energy into radiation as matter is crushed, heated, and accelerated. Both processes can be brilliant. Both can ionize gas. Both can leave emission lines in a spectrum. But they do not move the gas in the same way, and they do not shape the light with the same violence. A telescope image may blur these sources into similar red points. Spectroscopy is needed to separate them. Spectroscopy is the act of letting light confess its structure. Instead of measuring only how bright an object appears through a few broad filters, astronomers spread the light into a spectrum, arranging it by wavelength. In that spread-out light, atoms leave signatures. Hydrogen can mark its presence. Oxygen can mark its presence. Other elements can appear as lines. Bright, where gas emits light. Dark, where light is absorbed. The positions of those lines reveal redshift, because the lines appear at longer wavelengths than they would in a laboratory. Their strengths reveal the physical conditions of the gas. Their shapes reveal motion. This last clue is especially important for the quasar test, around a feeding supermassive black hole. Gas does not sit gently. It races in a deep gravitational well. Some of it moves toward the observer, some away, some across the line of sight, all at immense speeds. The effect is to broaden the spectral lines. A line that would be narrow in a calm cloud becomes smeared across a wider range of wavelengths. The broadening is not merely a technical detail. It is the fingerprint of fast motion near a powerful central mass. In a quasar, broad emission lines often reveal gas moving at thousands of kilometers per second. The line becomes wide because the emitting atoms are not sharing one calm velocity. They are part of a storm of orbital motion, inflow, outflow, and turbulence close to the black hole. The spectrum therefore carries a memory of the engine, even when the image shows only a point. This is why astronomers expected the compact red sources to expose themselves if they were quasars. Their images could be deceptive, but their spectra should be less so. If black holes dominated the light, the emission lines should show the mark of high-speed gas. If the gas were being lit by stars instead, the motion could be gentler, and the lines could be narrower. The difference is not always perfectly clean, because galaxies are complicated, but it gives a decisive path through the ambiguity. The red point must be asked not only how bright it is, but how its gas moves. For the Webb candidates, the expectation of broad lines made sense. Their compactness seemed almost made for a quasar explanation. Their distance made their luminosity more dramatic. Their redness placed them in an era when young galaxies, dense gas, and growing black holes could all coexist. An active nucleus could hide inside a small host, making the whole system appear much more mature than it really was. This would soften the challenge to galaxy formation. Instead of needing a billion stars packed into a tiny region, one could imagine a smaller stellar system with a bright black hole at its center. Instead of inventing an unusually dense mode of early galaxy growth, one could place the object into the known category of accretion-powered sources. The quasar hypothesis therefore carried a kind of comfort. It did not remove all mystery, because early black holes remain mysterious, but it moved the problem into a field that astronomy already understood how to investigate. The task was to look for the violent line shapes that such an engine should produce. Yet a good test is most valuable when it can fail. The spectrum is not required to protect the preferred explanation. It is allowed to contradict it. In the case of the compact red sources, that possibility became the turning point. The team examined the light for the marks of a central engine, for the broad features that would imply gas whipping around a black hole at extreme speeds. The point-like appearance had prepared the mind for that answer. The history of quasars had prepared the categories for that answer. The early universe itself, with its dense gas and rapid growth, seemed willing to allow that answer. But the light did not simply yield to expectation. It carried information of its own, quieter and more specific than the image. The question became whether the red points were loud in the spectrum, whether their gas had the velocity signature of accretion, whether the tiny objects were dominated by gravity's most efficient furnace. This is the narrow doorway through which the mystery passed. A visual point could still be a quasar. A red source could still be an active nucleus. A luminous ancient object could still be explained by a feeding black hole, but only if the spectrum agreed. When astronomy turns from the image to the broken-apart light, it moves from resemblance to evidence. The compact red sources had resembled quasars well enough to make the hypothesis unavoidable. They now had to survive the quasar test. In that test, the telescope was no longer asking how the objects looked, but what kind of motion lived inside their glow. The answer would decide whether Webb had found another face of black hole growth, or whether it had found something more difficult, galaxies so compact and bright that they had been mistaken for the engines that usually hide inside them. The spectrum answered with restraint, where a quasar would normally leave a broad and restless signature. The compact red sources showed lines that were unexpectedly narrow. This is a small observational detail with large consequences. In an astronomical image, a dot may deceive the eye, but a spectral line preserves the motion of the gas that produced it. When atoms emit light at particular wavelengths, they do so with a natural precision. In a calm cloud, the line remains relatively sharp, shifted by distance but not greatly smeared by internal speed. In a violent environment, the same line widens. Gas moving rapidly toward and away from the observer sends its light to slightly different wavelengths, and those differences blend into a broad feature. This broadening is one of the classic signs of gas near a feeding supermassive black hole. It is not merely brightness that reveals a quasar. It is motion. The compact red sources had seemed ready to become quasars because they were bright, distant, and unresolved. Their appearance invited the black hole explanation, yet their spectra did not carry the expected turbulence. The lines were not spread into the wide profiles of gas racing around a deep gravitational well. They appeared comparatively narrow, as if the emitting gas were moving with far less violence. This quietness changed the interpretation of the light. It suggested that the objects were not dominated by an active nucleus, but by stars and the gas those stars had illuminated. The difference is subtle in language and profound in physics. A black hole can make a small region shine with immense power by drawing matter inward and heating it through gravity. Young massive stars can also make gas shine, but through a different process. They pour out ultraviolet radiation, energetic light capable of stripping electrons from hydrogen and oxygen atoms in the surrounding gas. When those electrons recombine or when atoms settle into lower energy states, they emit light at specific wavelengths. A young star-forming region can therefore produce bright emission lines without needing the extreme motions of an accretion disk. The gas may be warm, ionized, and luminous, but not racing at the speeds expected near a black hole. Narrow lines are compatible with that calmer setting. They do not make the object ordinary, but they move the source of its brightness away from the most compact engine known and toward a population of young stars. In the case of the Webb objects, this distinction sharpened the mystery rather than resolving it. If the points were quasars, their small apparent size would be easy to understand. If they were star-forming galaxies, their small apparent size became much harder. The spectrum removed one kind of impossibility and left another behind. It did not say that nothing powerful was happening. It said that the power did not seem to be arranged like the familiar violence of a quasar. The gas spoke in narrow lines, and narrow lines imply that the light is not being smeared by extreme velocity. That does not mean the objects are still in a peaceful human sense. Star formation in the young universe can be fierce. Massive stars are born quickly, burn intensely, and de-young. Their radiation can carve bubbles in surrounding gas. Their winds can push material outward. Their explosions can enrich their environments with heavier elements, but compared with the immediate neighborhood of a feeding supermassive black hole, such regions can appear dynamically gentler. Their emission lines can remain tight enough to preserve a cleaner shape. The compact red sources, therefore, seem to contain energetic star formation without the spectral chaos of an active nucleus. They were bright, but not in the expected way. They were compact, but not because a black hole had compressed the visible signal into a point. They were distant, but not easily placed among the known beacons of the early universe. This is why the narrow lines matter so much. They force the objects to be taken seriously as galaxies, not merely as black hole glare. Once that shift is made, Every measurement becomes more demanding. The light must be attributed to stars across a finite region, not to a near-point engine. The brightness must be reconciled with a stellar population, not with accretion. The size must be interpreted as the physical compactness of a galaxy or galactic core, not the unresolved glow of a central black hole. A narrow spectral line becomes a doorway into a dense stellar system. It implies that the atoms responsible for the emission are not plunging through the extreme gravitational theater of an active nucleus, but are part of gas lit by hot young stars. Those stars must exist in large enough numbers to account for the observed luminosity. They must have formed early enough to shine at the redshift being measured. They must be packed closely enough that the whole system remains point-like to Webb. The line shape, then, is not a technical footnote. It is the hinge that turns a quasar candidate into a compact galaxy candidate. It changes the object from a known kind of distant point into a more unsettling kind of distant point. The calmness of the gas becomes evidence for a more difficult density. A quasar can conceal the host around it, making a galaxy look small because its center overwhelms the rest. A narrow-line star-forming system cannot use that same escape. It has to explain itself as matter turned into stars within an astonishingly limited volume. This is where the visual contradiction returns with greater force. The objects look like stars because their light is concentrated. Their spectra suggest that the light is produced by stars. The same word appears in two different senses, and the confusion deepens. They look stellar in shape, but not because they are single stars. They appear to be stellar in energy source, because stars may be powering the gas. The result is a galaxy that wears the image profile of a star while shining through the combined work of many stars. It is almost a reversal of the old quasar story. Quasars looked like stars, but were powered by black holes inside galaxies. These sources may look like stars, but be powered by dense newborn stellar populations that are themselves the galaxy. The category bends in a new direction. The absence of broad lines also gives a quieter character to the discovery. Many astronomical mysteries are framed around violence, explosion, collision, and devouring black holes. Here, the crucial clue is a lack of violence in the line shape. The gas is not silent, but it is not chaotic in the expected way. It is luminous without the broad smear of extreme speed. That restraint makes the objects stranger, not less strange. It suggests that the early universe may have built some of its densest systems through processes that did not immediately announce themselves as destruction. The light could come from concentrated starbirth, from gas collapsing and igniting in a tight region, from a young core forming with extraordinary efficiency. Such a scene would still be intense, but its signature would be ordered enough to preserve narrow emission. The discovery, therefore, asks for a careful imagination. Sometimes the most disruptive evidence is a narrow line where a broad one should have been. There are still cautions. Spectra of faint distant sources are difficult. Noise can shape interpretation. Dust, orientation, and limited signal can complicate the reading. A narrow line does not by itself prove that no black hole is present. A black hole may exist quietly in the center, too faint to dominate the light or too obscured to show the usual signature. The question is dominance. What is producing most of the observed glow? In these compact sources, the evidence points away from the familiar broadline quasar picture and towards stellar processes. This is a measured conclusion, not a final verdict. It leaves space for later data to refine the identity. More spectra and better models may reveal mixed systems, where young stars and modest black hole activity coexist. But the first decisive clue remains the same. The objects did not behave like the standard solution. They did not give astronomy the broad lines that would have made them easier to categorize. They remained compact red points, but with gas too calm for the role expected. That calmness widened the problem into galaxy formation itself. If these are galaxies, they are not familiar galaxies seen from far away. They are extremely compact arrangements of stars and gas at early times, dense enough to blur into points and luminous enough to be noticed across vast distance. Their spectra suggest that their light comes from young stellar populations, perhaps among the early builders of galactic cores. They may be moments when gas has collapsed efficiently into a central region before a larger envelope of stars has formed around it. In that case, the narrow lines are not only a rejection of the quasar explanation, they are evidence of a stage in galactic birth that had been hard to see because it looked too much like something else. Webb did not simply find a bright point and call it mysterious. It found a point whose light, when unfolded, failed to match the obvious answer. The gas was too quiet for the expected storm. The line was too narrow for the usual black hole story. And in that narrowness, the objects became larger in meaning, not smaller, carrying the possibility that some galaxies began as dense red seeds, shining through calm lines at the edge of time. If the narrow lines move the light away from a quasar, they move it toward a more difficult picture. The objects begin to look less like black holes, masquerading as stars, and more like galaxies compressed until they resemble stars. This is the central contradiction. A galaxy is not defined only by size, but size has always been part of how galaxies are imagined. Even the smallest familiar galaxies are roomy by human standards. Their stars are separated by immense darkness. Their gas drifts through wide volumes. Their shapes may be faint and ragged, but they still occupy space in a way that a telescope can often recognize. The compact red sources resist that recognition. If their light truly comes from young stars at great distance, then those stars must be gathered into regions of startling density. The mass implied by the brightness is not the mass of a lone star, nor of a simple stellar cluster. It suggests a system with the weight of a small galaxy, perhaps containing the combined light of hundreds of millions or billions of stars. Yet the image gives almost no width. It does not spread into a disk. It does not soften into a visible halo. It sits as a point, as though the galaxy has folded its early life into a dense central knot. This is not merely a matter of scale being hard to imagine. It is a physical challenge. Stars form from gas, and gas has pressure, turbulence, rotation, and heat. A cloud collapsing under gravity does not usually fall into a perfect point. It fragments, it spins, it forms clumps. Radiation from the first massive stars pushes against further collapse. Explosions from dying stars stir the surrounding material. Young galaxies should therefore be messy, with star formation scattered through irregular regions and gas flowing in and out. To place so much stellar material inside only a few dozen light-years asks for conditions far more efficient than the familiar picture. It asks how gas could lose energy and angular momentum quickly enough to crowd into the center. It asks how star formation could proceed so intensely without tearing the system apart. It asks why the result does not immediately resemble a black hole-dominated object, even though the density seems to invite collapse. The narrow spectral lines make the question sharper because they suggest that the light is not simply the glare of matter falling into a central abyss. The stars themselves, or the gas lit by them, must carry much of the observed signal. That means the compactness belongs to the stellar system, not only to a hidden engine. A useful comparison is a globular cluster, one of the dense old swarms of stars that orbit large galaxies today. Globular clusters can pack many stars into a small region, creating brilliant crowded centers. But they are not usually as massive as galaxies, and they are not normally treated as the main body of a forming galaxy. The Webb objects seem to go beyond that familiar category. They may resemble star clusters in compactness, while reaching toward galaxies in mass and cosmic role. They blur the border between a cluster and a galaxy in the same way they blur the border between a point source and an extended system. The universe may be showing a phase when the central stellar body of a future galaxy is being assembled in an extremely condensed form. Before later, growth adds a broader envelope around it. In that interpretation, the red dot is not the whole mature galaxy. It is the dense seed, the nucleus, the first concentrated heart of a system that may later expand through accretion and merger. What looks incomplete in shape may be early in sequence. What looks too small may be a beginning rather than an error. Density changes everything inside such a place. In the region around the Sun, stars are separated by several light years on average. The night sky is dark because most stars are far away, and because empty space dominates the volume between them. In a compact early galaxy, the distances between neighboring stars could be far smaller. Starlight would overlap, radiation would fill the environment, gas would be ionized by many young massive stars at once. Stellar winds and supernovae would interact in tight quarters, stirring the gas with repeated shocks. Packing a galaxy into a few dozen light years creates an environment where the separation between individual stellar lives becomes less important than the collective field of light and gravity. The system becomes a furnace of formation, an early galactic core burning through its gas with remarkable speed. The same compactness that makes it look like a star to Webb would make it internally crowded beyond ordinary galactic intuition. Such density also presses against theories of survival. A very dense cluster of stars evolves dynamically. Stars pass near one another. Their orbits exchange energy. Some may be flung outward. Massive stars sink toward the center through interactions. Gas can be expelled by radiation and explosions, reducing the material available for later star formation. If the core is too dense and massive, gravitational collapse may feed a central black hole or help build one rapidly. These processes do not forbid compact galaxies, but they make them active and unstable places. A dense stellar seed may not remain unchanged for long. It may puff outward after gas is expelled. It may merge with other systems. It may become the nucleus of a larger galaxy. This is one reason the Webb sources matter. They may be temporary forms, visible only during a short phase in the young universe. If telescopes miss that phase, the later universe preserves only the outcome, not the beginning. The red points could be snapshots of a stage that normally passes too quickly and too far away to recognize. The contradiction with ordinary appearance is therefore not a simple mistake. It is a clue to timing. A forming galaxy does not have to pass through a stage that looks like a miniature spiral. It may pass first through a stage that looks like a star because the star-forming material has fallen into the center before the rest of the galaxy has become visible. Later, as more gas arrives and mergers add outer stars, the object may gain the extended shape expected of a galaxy. But in the moment Webb observes, the system is dominated by its core. The outskirts may be too faint, too young, too diffuse, or not yet assembled. The telescope receives the central brightness and records a point. The category of galaxy then becomes less about visible width and more about gravitational and stellar content. A galaxy can be present before it looks like one. This idea is unsettling because it asks astronomy to separate identity from appearance. The same object, at a later age, might be obvious. At its beginning, it can be nearly hidden by compactness. There is also a question of how such systems can form so early. The universe at that time was denser than it is now, and gas was more available to collapse into dark matter halos, the invisible gravitational scaffolds where galaxies grow. If cold streams of gas flowed efficiently into the center of a halo, they could feed rapid star formation in a confined region. If cooling was effective and angular momentum was transported away, the gas could collect into a dense nucleus. But each part of that sentence contains a difficult physical process. Gas must arrive without being heated too much. It must shed enough motion to fall inward. It must form stars rapidly, but not so rapidly that feedback stops the inflow at once. Dark matter must provide a deep enough well, yet the visible system must remain extraordinarily small. The compact red sources are therefore not just surprising objects. They are boundary conditions for theory. They tell models of galaxy formation how extreme the early universe may have been allowed to become. A theory that cannot make them, if they are confirmed, is missing a channel of growth. A theory that can make them must explain why they are visible as red points and how they evolve into later populations. The image gives the mystery its simplicity. A red dot appears where a galaxy may be hiding. The spectrum gives the mystery its discipline. Narrow lines suggest stars and calmer gas, not a broad line quasar. The inferred mass gives the mystery its weight. There may be far too much stellar material inside, far too little space. Together, these facts create the picture of galaxies packed like stars, not because they are small in importance, but because their earliest luminous bodies may be condensed almost beyond recognition. The phrase sounds contradictory only because the older categories are being stretched. A star is a point because it is physically compact and nearby enough to be unresolved. These galaxies may be points because distance and density have conspired to hide their structure. They are not stars, yet they borrow the star's appearance. They are galaxies, yet they lack the visible spaciousness normally associated with the word. In that borrowed appearance, Webb has found a challenge to cosmic common sense. The early universe may have built some of its first lasting structures not as wide, faint clouds, but as brilliant, crowded seeds, too dense to look like galaxies and too galactic to be dismissed as stars. The compact red sources become most difficult when they are placed back into time. A strange object in the nearby universe can often be explained by age. There has been enough time for gravity to build complexity, enough time for mergers to pile one system onto another, enough time for gas to cool, stars to form, and galaxies to settle into unusual shapes. But the Webb objects appear to belong to a much younger cosmic setting. Their light may have begun its journey when the universe was still close to its dawn, when the first long chapters of galaxy formation had barely opened. That early placement turns their compactness and mass into a timeline problem. A galaxy can be dense today because it has lived through many stages. It can be massive because it has consumed smaller systems, gathered gas over billions of years, and survived repeated transformations. In the early universe, that long history has not yet happened. The clock is shorter. The available time is narrower. Every inferred star, every measure of brightness, every hint of chemical enrichment has to fit inside a young cosmos. The red points, therefore, ask a simple and severe question. How can a system that looks so small and seems so full have formed so soon? Standard galaxy formation is often described as hierarchical, meaning that large structures grow from smaller ones. In this view, the first matter does not immediately become a grand galaxy. It gathers into dark matter halos, invisible gravitational wells where gas can collect. Small halos merge into larger halos. Gas falls inward, heats, cools, fragments. and form stars. Early star clusters and dwarf-like systems collide and blend. Over time, through many such mergers and accretion events, larger galaxies emerge. The process is not smooth in every detail, but the broad direction is clear. The universe builds upward. Small things assemble into bigger things. This picture has deep support because it follows naturally from gravity, acting on the slight unevenness present in the early universe. Regions a little denser than average pull in more matter. Their gravity strengthens. They merge with neighbors. Structure grows like a cosmic web, thickening at its knots. The problem is that this process, even when efficient, still needs time. Matter cannot cross space instantly. Gas cannot cool without physics taking its course. Stars cannot form before enough material has gathered. Mergers require orbits, encounters, and repeated gravitational sorting. The compact red sources seem to compress too many outcomes into too little cosmic time. Their apparent maturity is not maturity in the calm visual sense of a settled spiral or a broad elliptical galaxy. It is maturity in density and stellar content. If they truly contain large populations of young stars in tight regions, then the early universe managed to build intense stellar systems very rapidly. They are not necessarily old objects, but they look advanced in one key way. They have gathered and transformed a significant amount of gas into luminous stars before the ordinary story has had much room to breathe. This is why they can be compared, gently, to adults standing in a nursery. They belong to an epoch when galaxies are expected to be small, messy, and incomplete. Yet they carry signs of concentrated growth. The comparison is imperfect, because they may be young in their own internal histories, filled with newly formed stars rather than ancient ones. But the discomfort remains. They seem too organized by density, too efficient in star formation, too bright for their apparent size and age. The universe appears to have skipped some visible steps, or to have taken a faster path that current models do not fully capture. The tension becomes clearer when considering what star formation requires. Gas must become dense enough to collapse under gravity. It must cool, because hot gas resists collapse through pressure. It must gather in a place where gravity can overcome turbulence, rotation, magnetic fields, and feedback from the first stars that ignite. Once massive stars form, they begin to work against the very process that made them. Their radiation heats surrounding gas. Their winds push material outward. Their deaths as supernovae inject energy into the system. In a small early galaxy, feedback can be especially disruptive. It can blow gas out of the shallow gravitational well before many more stars are born. For a compact red source to become so dense, the inflow of gas must have been strong enough, and the gravitational well deep enough, to keep feeding star formation despite these opposing forces. This is a demanding requirement. It does not make the objects impossible, but it forces the theory to become more specific. The old general statement that galaxies grow from small things is no longer enough. The models must explain how the gas moved, how quickly it cooled, how concentrated it became, and why feedback did not immediately scatter it. Another part of the timeline problem involves chemical evidence. Very early stars begin with simple ingredients, mainly hydrogen and helium, because heavier elements are forged inside stars and scattered by stellar deaths. A galaxy showing signs of elements, such as oxygen, has already passed through some cycle of stellar processing. Massive stars can live briefly and enrich their surroundings quickly. So, chemical signatures in the early universe are not automatically impossible, but they still add weight to the clock. There must have been time for stars to form, shine, and seed the surrounding gas with heavier atoms. If compact red objects show such signatures while also sitting at high redshift, they are telling a story of rapid enrichment in a small volume. That story is plausible only if star formation was intense and early. It implies that these systems were not simply gathering gas in preparation for future growth. They had already begun the work of turning primordial material into a more chemically complex environment. The early cosmos, in this view, is not a slow dark room where the first lights appear hesitantly. It is a place where some knots of matter ignite quickly, process gas rapidly, and become dense enough to challenge the pace expected from ordinary assembly. Hierarchical growth can be adjusted. It is not a fragile idea that collapses at the first strange discovery. The universe can build some objects faster than average. Dense regions of the cosmic web can form earlier than quieter regions. Gravitational lensing can make distant objects easier to detect and may bias observations toward brighter, denser cases. Measurements of mass and size can change as better data arrives. Some candidates may later turn out to be less massive, less distant, dustier, or more influenced by hidden black holes than first believed. These cautions matter. The timeline problem is not proof that the standard model is broken beyond repair. It is pressure on the details. A strong scientific model should not merely explain the average galaxy. It should also account for the extreme objects that appear at the edge of observation. The compact red sources may be rare peaks. Systems born in unusually dense environments where gas flowed inward with exceptional efficiency, or they may be signs of a broader population that previous surveys missed. The difference is enormous. A few rare outliers can be absorbed into a flexible theory. A common population of dense early galaxies would demand a deeper revision of how rapidly the young universe formed structure. This is why the number of such objects matters. One compact red source can be an anomaly. A handful can be a puzzle. Dozens across a small field begin to hint at a pattern. If future surveys find many more, the timeline problem expands from an object-by-object curiosity into a census problem. The early universe would contain more concentrated stellar mass than expected, hidden in sources too compact to have been counted properly before. That would affect estimates of how quickly the first galaxies formed stars, how early they enriched their surroundings, and how they contributed to the changing transparency of the cosmos. Early stars and galaxies helped reionize the universe, clearing the fog of neutral hydrogen that filled space after the first atoms formed. Compact, dense galaxies could have played a role in that transformation, depending on how much ionizing radiation escaped them. Thus, the red points might not be isolated oddities. They may connect to one of the largest transitions in cosmic history. The period when the universe became filled with sources capable of reshaping the space between galaxies. The timeline problem is therefore also a problem of ancestry. What do these compact systems become if they are dense seeds? They may later grow into the central regions of massive galaxies. Their stars may survive as ancient cores buried inside larger structures. Their early compactness may be erased by later mergers, leaving only indirect traces in the centers of present-day galaxies. This possibility softens one mystery while deepening another. It suggests that the red points are not failed galaxies or cosmic mistakes, but early phases of objects that later become familiar. The young universe may have built hearts before bodies, dense centers before broad halos, inner light before outer structure. If so, the timeline is not necessarily too short for all growth. It is too short only for the slow assembly path that begins with extended forms. A faster inward-building path may have operated alongside the familiar merger-driven one. The red sources stand at the place where those paths must be compared. Their existence asks whether galaxy formation is best imagined as gradual assembly alone, or as a mixture of violent merging and rapid central collapse. The answer is still forming, carried in faint spectra and tiny points of infrared light. But the challenge has already changed the mood of the early universe. It no longer appears as a simple infancy where everything waits to grow. It appears as an environment capable of sudden concentration, where matter found deep wells. Gas streamed inward, and stars gathered in crowded cores before the wider galactic shapes had time to unfold. Webb's red points are small on the image, but they make the cosmic clock feel tighter. They suggest that the first great structures did not merely begin early. Some of them may have begun with startling efficiency, racing ahead of the expected schedule while still hiding in the shape of a star. A faster path to a dense early galaxy begins with gas. Stars are the visible result, but gas is the material out of which the first visible structures are made. In the standard picture, gas falls into the gravity well of a growing dark matter halo and is often heated as it enters. It can form a hot atmosphere around the young galaxy, a reservoir that must cool before it can sink inward and make stars. Cooling takes time. In a young universe where the clock is already tight, that delay matters. The compact red sources suggest that, at least in some places, the delay may have been bypassed. The possible path is often described as cold or quiet accretion. The word quiet does not mean weak, and it does not mean motionless. It means that growth can happen without relying mainly on violent collisions between already formed galaxies. It means that gas can stream inward along the filaments of the cosmic web, guided by dark matter, feeding the center of a young halo with unusual efficiency. Instead of building a galaxy by repeatedly smashing smaller stellar systems together, the universe may pump raw material directly into the region where the first dense core is forming. In the early cosmos, the cosmic web was not an empty background. It was the architecture of matter itself. Dark matter gathered into long filaments and knots, and ordinary gas followed its gravity. Where filaments crossed, halos grew. Where halos deepened, gas could collect. In massive enough halos, the falling gas might be shocked and heated, forming the kind of hot envelope that slows later star formation. But in certain early conditions, narrow streams of relatively cool gas could penetrate deeper before being fully heated. These streams would not behave like gentle rivers in a peaceful landscape. They would be immense flows of primordial material, shaped by gravity and pressure, converging through space toward a young center. Yet compared with a major galactic collision, they would be smooth. They would bring fuel without first scattering it through a large, messy structure. They could keep feeding the core while stars were already forming there. This is why cold inflow is so important for the red points. It offers a way to concentrate matter quickly without waiting for many separate galaxies to assemble and merge. It turns the problem from one of collision timing into one of gas delivery. If gas can arrive fast enough, cool enough, and deep enough, a dense stellar seed can grow on a schedule that would otherwise seem too short. The image of inside-out growth is useful, as long as it is kept simple. A mature galaxy often has a visible body, a broad distribution of stars around a central region. The compact red sources may represent a stage before that body is fully built. Their central regions could be growing first, fed by streams that fall toward the deepest part of the gravitational well. Stars ignite in the core while the outskirts remain faint, sparse, or absent. The telescope sees the core because it is bright. It misses the envelope because it has not formed or because it is too dim to resolve. In such a system, the apparent point is not a finished galaxy squeezed into a permanent miniature form. It is an early nucleus, a concentrated beginning. Later, Additional gas may settle into wider structures. Smaller systems may merge with it. Stars may be added at larger radii. Feedback from young stars may push some material outward and make the whole system expand. But at the moment, Webb observes it. The dominant light comes from the center. The galaxy is still becoming broad. Its first act is dense. This kind of growth helps explain why the objects might look visually misleading. A galaxy built from the outside through many mergers may show irregular shapes, extended star-forming knots, and diffuse structure. A galaxy fed through narrow streams into its heart may produce a luminous compact core before its surroundings become obvious. The two histories could lead to different appearances at the same cosmic age. One would look messy and spread out. The other would look like a red point. Both could be real. Galaxy formation would then be less like a single road and more like a landscape with several channels. Some systems grow by collision. Some grow by steady inflow. Some likely do both, with the balance changing according to mass, environment, and time. The compact red sources may be the visible tips of the quiet channel, places where smooth gas delivery became so efficient that the first stars crowded into a small volume before the galaxy acquired a familiar shape. This does not remove the mystery. It gives the mystery a possible mechanism. The physics still has to satisfy hard requirements. The gas must lose enough angular momentum, the tendency to keep orbiting rather than falling straight inward. If it cannot shed that motion, it forms a larger rotating structure instead of a compact core. The gas must cool despite the radiation from new stars. It must remain bound even as massive stars heat and push against it. It must keep flowing after the first explosions begin to disturb the region. The dark matter halo must be massive enough to hold on to the material, but the visible galaxy must remain small enough to match the observations. Each condition narrows the range of possible histories. Quiet accretion is not a magic phrase that solves every contradiction. It is a candidate process that can be tested by asking whether simulations can produce objects with the right masses, sizes, colors, and line strengths at the right time. The red points are valuable because they force these tests to become sharper. They demand not just early galaxies, but early galaxies with concentrated light and calm enough gas to avoid the broad line quasar signature. There is also a deeper consequence. If cold inflow can build dense cores rapidly, then the earliest galaxies may have been more efficient engines of transformation than previously assumed. They would take simple gas from the young universe and turn it into massive stars, ionized clouds, heavier elements, and perhaps the seeds of central black holes. A dense core is a powerful environment for all of these processes. Massive stars live quickly and die quickly, enriching their surroundings. Gas driven inward can feed starbursts and may eventually feed black holes. Stellar interactions may become more common in crowded regions. Radiation from the core may leak into surrounding space, helping change the state of the intergalactic gas. The compact red sources, therefore, may not be only witnesses to galaxy formation. They may be participants in the larger transition that made the universe brighter, more chemically complex, and more transparent to light. A small object on an image can represent a concentrated workshop where the early cosmos is being altered at high speed. The quietness of the term should not soften the scale of the event. Quiet accretion is quiet, only compared with the drama of collision. It is still gravity organizing matter across enormous distances. It is still gas falling through the invisible scaffolding of dark matter. It is still star formation igniting in crowded waves. What makes it quiet is the absence of an obvious crash. The possibility that a galaxy can grow powerfully without first displaying the violent visual signatures that would make it easy to recognize. This matches the mood of the compact red sources. They do not look violent in the image. They do not spread into shattered forms. Their spectra may lack the broad lines of a central storm. Yet beneath that calm appearance, a rapid inward flow may be building a dense stellar core. The discovery, therefore, asks for a more subtle imagination of early growth, one in which efficiency can be hidden under simplicity, and intensity can appear as a dot. If this interpretation is right, the red points may be among the first visible hearts of future galaxies. They may not remain compact forever. Time will work on them. Gas inflow may continue. Mergers may add stars. Feedback may loosen the central density. The growing system may develop a broader halo of stars and eventually resemble a more familiar galaxy. Its early point-like phase could become buried inside later structure, preserved only as an ancient central population. Looking at such an object with Webb would then be like seeing the heart before the body, the nucleus before the envelope, the first bright knot before the surrounding galaxy takes shape. The timeline problem becomes less impossible, though still difficult. The universe would not need to wait for countless collisions to build the first dense centers. It could feed them directly. Through cold streams and inward collapse, matter could arrive where gravity was deepest, and stars could ignite there in a compressed beginning. The compact red sources remain uncertain, but quiet accretion gives them a path through the young cosmic web. It suggests that the early universe may have had a fast, inward, almost hidden way of building galaxies, not by assembling only from the outside, and not always by announcing itself through chaos, but by drawing gas down the filaments of darkness and lighting it in the center until a future galaxy first appeared as a single red point. The possibility of a ghost population changes the discovery from a set of strange objects into a problem of cosmic accounting. A single compact red source can be treated as an oddity. A few can be treated as a puzzle. But if many such sources exist, and if many of them have been overlooked because they resemble stars, then the early universe may have been systematically undercounted. Astronomy does not only ask what objects are, it asks how many there are, how often they form, how much light they produce, how much mass they contain, and how they change the space around them. Every census depends on the rules used to count. If the rules quietly remove a class of objects before the counting begins, then the resulting history becomes incomplete. The compact red points are unsettling because they may have been present in earlier observations without being recognized as galaxies. Their disguise is simple. They are small on the image. They are sharp enough to resemble foreground stars. They lack the extended glow that galaxy searches often expect. In a survey pipeline, that is enough to make them vanish from the scientific story. Not from the image itself, necessarily, but from the catalog where measured objects become evidence. Once an object is labeled as stellar contamination, ambiguous noise, or a failed candidate, it stops helping to define the early universe. It remains in the data, but not in the narrative. This is how a ghost population can exist in science. It is not invisible in the strict sense. It is unseen because the method of seeing has taught itself not to look. Astronomers have to remove foreground stars to study distant galaxies. They have to reject sources with uncertain shapes, poor signal, or confusing colors. They have to guard against artifacts created by detectors, cosmic rays, processing errors, and blended light from neighboring objects. A survey without filters would drown in false positives. But the filters are built from prior knowledge, and prior knowledge is always shaped by what previous instruments could reveal. Before Webb, many early galaxies were expected to appear as faint, extended smudges, or as lensed arcs. not as sharp red points with the physical meaning of dense galactic cores. So the rules favored what was already plausible. A galaxy should have width. A star should be point-like. A distant active black hole could be point-like. But then its spectrum should show the proper signs. The compact red sources complicate every part of that logic. They suggest that an object can be a galaxy while lacking an obvious galaxy shape, and that the earliest stages of galactic growth may not resemble the forms most familiar from later cosmic time. If this is true, then old catalogs may not simply be missing faint objects beyond the reach of their telescopes. They may be missing objects that were within reach, but placed in the wrong category. Such misclassification has consequences. The early universe is reconstructed statistically. No telescope sees the whole sky to infinite depth. Instead, astronomers observe selected fields, measure the objects in them, correct for selection effects, and infer broader populations. The number of galaxies at a given redshift helps estimate how fast structure formed. Their brightness helps estimate the rate of star formation. Their colors and spectra help estimate age, dust, chemical enrichment, and the energy escaping into surrounding space. If compact galaxies were filtered out because they looked stellar, then all of those estimates may need adjustment. The correction may be modest if the sources are rare. It may be substantial if they are common. The most provocative hints come from the fact that deep fields cover tiny areas of the sky. A small patch that contains several compact red candidates can imply a much larger hidden population when scaled across the celestial sphere. Scaling is always dangerous and must be done carefully, because small fields can sample unusual regions and because lensing can magnify some sources more than others. Still, the hint is enough to matter. If the first searches find these objects in a narrow window, then they are probably not unique accidents. They may be a recurring feature of early cosmic structure, waiting in other fields, other archives, and other surveys under names that fail to capture what they are. The phrase ghost population also carries another meaning. These objects may be ghosts of future galaxies, early dense forms whose later descendants are still present, but no longer recognizable in the same way. A compact core in the young universe may grow into the center of a much larger galaxy. Later, mergers may surround it with outer stars. Gas inflow may continue. Feedback may expand or reshape the original density. By the present day, the small red point would no longer exist as a separate visible category. Its stars may be buried inside the central regions of massive galaxies, mixed into old bulges or dense nuclei. The early phase would be gone, not because the object disappeared, but because it evolved. That makes direct observation especially valuable. Webb may be catching a short-lived stage, a stage that cannot easily be inferred from the mature universe alone. If old stars in a nearby galaxy carry the chemical memory of a dense beginning, that memory is difficult to decode. A direct view of the compact phase gives theory a living fossil from deep time, a form that later growth usually hides. Revisiting the archives becomes a kind of excavation. The data from older telescopes may not match Webb in sensitivity or wavelength coverage, but it can still contain clues. Some compact red candidates may have faint counterparts in Hubble fields. Some may appear in infrared surveys from earlier missions. Some may have been classified as stars, uncertain red sources, or low-priority artifacts. Reanalysis requires new questions. Instead of asking only where extended high redshift galaxies are, researchers can ask which point-like sources have colors inconsistent with ordinary Milky Way stars. Instead of rejecting compactness as contamination, they can combine it with redshift indicators and spectral tests. This does not mean every old point becomes mysterious. The majority will still be mundane. The change is not a collapse of standards, but a widening of attention. A clean catalog remains important, but so does a catalog designed to preserve category breakers. Different scientific goals require different filters. The mistake would be to let one goal, such as removing foreground stars, quietly erase another, such as discovering compact early galaxies. The ghost population reminds astronomy that absence in a catalog is not the same as absence in the universe. This lesson has appeared before in different forms. Every instrument sees through its own biases. Radio telescopes revealed cold gas and energetic jets that optical surveys could miss. Infrared astronomy revealed dust-hidden stars and galaxies invisible in blue light. X-ray astronomy revealed hot gas, collapsed objects, and violent accretion. Each new window did more than add objects. It changed the definition of what counted as important. Webb is creating a similar change for the ancient infrared universe. It reveals not only fainter galaxies, but forms of galaxy that older expectations may have treated as unlikely. The compact red points are especially powerful because their bias is not only technological, it is conceptual. They were hidden by the assumption that visual extent is a reliable sign of galactic identity. Once that assumption weakens, the sky becomes less settled. A point can be reconsidered. A red speck can become a candidate dense core. A source once removed for being too star-like can become evidence for how stars gathered when the universe was young. The practical work ahead is careful and repetitive. More fields must be searched. More spectra must be taken. The objects must be separated from brown dwarfs, dusty interlopers, lensed background sources, and active nuclei. Their masses and sizes must be estimated with models that admit uncertainty. Simulations must test whether cold inflow, rapid cooling, and intense star formation can produce such compact systems in sufficient numbers. The search must also ask whether the sample is biased toward the brightest and densest examples, because those are the ones easiest to see. A hidden population can be overestimated as well as underestimated. The goal is not to make the universe more mysterious than the evidence allows. It is to let the evidence change the questions. If the compact red sources endure under these tests, then the census of the early universe becomes richer and more crowded. The first galaxies were not only faint, irregular smudges and brilliant quasars, some were dense red seeds, compact enough to pass as stars, luminous enough to mark intense stellar birth, and numerous enough to reshape the count of early structure. In that revised picture, the young cosmos is less empty and less slow. It contains hidden workshops of formation, packed into small volumes and scattered across the deep fields like embers. The mystery of the ghost population is therefore a mystery of recognition. Nature did not necessarily conceal these objects by making them dark. It concealed them by making them familiar. They wore the shape of points in a science that had learned to distrust points. They survived in images while disappearing from interpretation. Webb's discovery asks that the old images be read again with softer assumptions and sharper tools. The universe may have been telling this story for years in a language of tiny red dots. Only now has the question changed enough for those dots to answer. The name platypus galaxies carries a softness that can almost hide how disruptive the idea is. It is not an official final category, and it may change as the evidence becomes clearer. But the nickname works because it points to a familiar kind of confusion. The platypus did not become strange because nature had made a mistake. It became strange because observers tried to place it inside boxes that were too narrow. It looked like several animals at once, and the older categories strained under the weight of a real creature. The compact red sources found by Webb create a similar pressure in astronomy. They do not fit comfortably as stars. because their colors and inferred distances pull them toward the ancient universe. They do not fit comfortably as ordinary galaxies, because their images remain too sharp and small. They do not fit comfortably as quasars, because the expected broad signatures of violent black hole activity may be absent or weak. They are not outside nature. They are outside a convenient arrangement of names. That distinction matters. A category is not a law of physics. It is a tool that helps the mind move through a universe too large to hold all at once. When the tool stops fitting the object is not the thing that must yield. The tool must be remade. For a long time, astronomy could rely on a visual grammar that seemed stable. Stars were points. Galaxies were extended forms. Nebulae were clouds. Clusters were gatherings. Black holes were inferred through motion, radiation, and the behavior of surrounding matter. These distinctions still matter, and most of them still work most of the time. But the deep universe has a way of revealing the edges of familiar grammar. At great distance, light is stretched, structure is blurred, and time itself enters the image. A galaxy in its first dense phase may not look like a galaxy built through billions of years of later growth. A young core may shine before a wider body forms around it. A crowded system of stars may collapse into a point in the telescope not because it is a single star, but because distance and density have made its structure too small to resolve. Webb's red points live in this uneasy place. They ask astronomy to define a galaxy not only by visible width, but by its physical content, its history, its dark matter setting, its star formation, and its role in cosmic growth. In that broader sense, a galaxy may begin before it becomes visually generous. It may first appear as a dense seed, a red mark in the infrared dark, a concentrated beginning that later time will unfold. The platypus comparison also carries a warning against embarrassment. The first reaction to a category breaker is often suspicion. Perhaps the measurement is wrong. Perhaps the object is a blend. Perhaps the spectrum is noisy. Perhaps the red color is caused by dust or by a cool foreground body. These doubts are not obstacles to science. They are science doing its careful work. A discovery becomes strong only by surviving them. The compact red sources must continue to face that scrutiny. More spectra are needed. Better size measurements are needed. Independent fields must be searched. Models must test whether cold inflow, rapid cooling, and intense star formation can truly build such systems early enough. Some candidates may fall away. Some may turn out to be active nuclei, brown dwarfs, dusty galaxies, or artifacts of selection. The mystery does not require every red point to remain exotic. It requires only that a real population survives the tests. If it does, then the early universe contains a mode of galaxy formation that was easier to miss than to imagine. The challenge would not be that Webb found a few odd specks. The challenge would be that those specks represent a hidden phase of galactic birth, one that older filters and older expectations were poorly prepared to count. There is a calm humility in that possibility. The universe is not obligated to follow the sequence that seems most natural from nearby examples. The galaxies seen around the Milky Way today are mature or aging systems, shaped by long histories. They are the outcomes of time. From them, astronomers infer beginnings. But an outcome does not always reveal the path that produced it. A dense core in the young universe may later become buried under layers of accreted stars. Its early compactness may vanish inside a larger body. Its first violent season of star formation may leave only chemical traces. Looking only at the later galaxy is like looking at an ancient tree and trying to reconstruct the moment the seed first opened in darkness. Webb gives astronomy a direct glimpse closer to that seed stage. The compact red points may be small because they are young, dense, because the gas of the early cosmos flowed efficiently inward, and red because their light has crossed nearly all of cosmic history. They may be the first hearts of galaxies, not yet surrounded by the full structures that will one day make them recognizable. This does not make the standard picture useless. It makes it richer. Hierarchical growth, mergers, dark matter, halos, gas cooling, stellar feedback, and black hole growth all remain part of the story. The compact sources may add another thread, a fast inward channel in which matter streams through the cosmic web and builds central stellar mass before the outer galaxy becomes visible. They may show that early growth was not simply slow assembly from the outside, but also sudden concentration at the center. Such a thread could connect many puzzles. It could help explain how dense galactic cores appeared so early. It could provide environments where black hole seeds grow rapidly. It could alter estimates of early star formation and chemical enrichment. It could change how astronomers count the sources that helped illuminate and ionize the young universe. A tiny red dot, if multiplied across many fields, becomes not a curiosity, but a component of cosmic history. The scale of the question expands quietly. What began as a strange source classification becomes a possible revision to the early census of light. Yet the most lasting meaning of these objects may be methodological. They show that discovery often begins where procedure becomes too confident. Algorithms are necessary. Catalogs are necessary. Selection rules are necessary. Without them, deep field astronomy would be a sea of ambiguity. But the rules must remain open to revision, especially when new instruments enter new territory. Webb has made the infrared sky more detailed, and with that detail comes a responsibility to notice what older habits would discard. The point source cannot always be treated as boring. The red speck cannot always be treated as contamination. The absence of visible fuzz cannot always be treated as the absence of a galaxy. In the deepest fields, appearance is compressed by time, distance, and the limits of resolution. Meaning has to be assembled from many clues at once. The compact red sources reward that patience. They remind astronomy that a small mark in an image can contain questions about gas dynamics, stellar birth, black hole growth, cosmic expansion, and the reliability of the categories used to study them. As Webb continues to observe, the number of known candidates will change. Some mysteries will fade under better data, while others will sharpen. That is the normal rhythm of science. The important point is not that every early claim remains untouched. It is that the telescope has opened a region of possibility that had been closed by assumption. Future observations may reveal that the compact red points are diverse rather than uniform, with some powered mostly by stars, some by hidden black holes, and some by mixtures still difficult to separate. Their nickname may eventually give way to more precise language, but the first impression will remain valuable because it captures the moment when nature crossed a human boundary. A star-like image carried galactic meaning. A galaxy-like spectrum came from a point. A distant ancient object wore the simplest possible shape. In that crossing, the early universe became less familiar and more alive. The final wonder is not only that such objects may exist, it is that they may have been waiting in plain sight, scattered through deep images like quiet red embers. They ask for a science patient enough to look again at what had been set aside. They ask for definitions that bend without breaking. They ask for models that can hold both violence and quietness, collision and smooth inflow, mature structure and hidden beginnings. The platypus galaxies. If that name continues to follow them, are reminders that the universe does not begin with human categories. It begins with matter, gravity, light, and time. Categories come later, after the photons arrive and the mind tries to arrange them. Webb has delivered photons from a realm where that arrangement is still uncertain. In their narrow lines, their deep redness, and their unresolved shapes. These objects carry a gentle refusal. They refuse to be only stars. They refuse to look like ordinary galaxies. They refuse to let the early universe remain simple. A red point, almost nothing to the eye, becomes a doorway. Beyond it lies a cosmos that builds in more than one way, hides its beginnings inside familiar forms, and keeps teaching astronomy the same quiet lesson. The sky is not made to fit the map. The map is made again whenever the sky becomes stranger. The red points remain in the dark fields, small enough to seem almost weightless, yet carrying the pressure of deep time. They are not loud discoveries. They do not arrive as grand spirals or blazing arcs or shattered clouds of stars. They appear almost gently, as compact embers in the infrared, asking astronomy to slow down and look again. Their meaning is still being shaped by spectra, models, and future observations. Some may change identity as better data arrives. Some may become less strange. Others may become even more important. That is the quiet rhythm of science at the edge of knowledge. A mystery is not a failure of understanding. It is the place where understanding is still alive, still flexible, still willing to grow. The James Webb Space Telescope has not only looked farther into the universe, it has looked into an earlier grammar of structure, when galaxies may not yet have worn the forms that make them easy to name. In that young cosmos, matter may have flowed inward along dark filaments. Gas may have cooled in hidden centers, and stars may have gathered so densely that entire beginnings could masquerade as points. What seems small in an image may be vast in consequence. What seems familiar may be disguising a new category. The sky keeps its patience. It lets light travel for billions of years before it reaches a mirror. And when it arrives, it does not explain itself all at once. It offers a color, a line, a faint shape, a contradiction. From these fragments, the map is made again. Somewhere in those red dots is the memory of galaxies before they became spacious, before they became graceful, before they became obvious. The mystery remains open, soft, and distant, glowing at the edge of time.